The universe was once a silent sea of darkness. For millions of years, an impenetrable fog of hydrogen gas filled all of space. Then, a cosmic dawn arrived, a violent and beautiful transformation that ripped the veil apart. This was the Cosmic Reionization Era, the universe's greatest awakening, and its story is still being decoded. By the end of this journey, you will understand the 25 profound mysteries that define this pivotal cosmic chapter. We will explore what shattered the universal silence and why the first starlight remains so elusive. What cosmic event do you think could erase the stars from the sky? Our universe was born in fire, but it was the first light that truly gave it life. The greatest mystery of the reionization era is the identity of the cosmic pioneers whose rays first pierced the universal gloom. What were the objects that ended the Dark Ages? The prime suspects are threefold, each a titan in its own right. First, there are the legendary population 3 stars. These were not like the stars we see today. They were behemoths, the universe's first generation, forged from nothing but pristine hydrogen and helium. Imagine a star so massive it would make our sun look like a speck. These monsters burned hot and fast, flooding the cosmos with a ferocious, ionizing light, only to die in spectacular supernova explosions after just a few million years. They are the ghosts of the early cosmos, and we have never directly seen one. The second suspect is early galaxies, vast factories of newborn stars. While individual stars might be faint, a whole galaxy of them could generate a powerful collective glow, a steady leak of ultraviolet radiation that could slowly eat away at the surrounding fog of neutral hydrogen. Then there are the quasars, the most violent and energetic objects in the universe. Powered by ravenous supermassive black holes at the centers of young galaxies, quasars are like cosmic lighthouses, beaming out intense, focused jets of radiation capable of carving vast, ionized bubbles in the primordial gas. So who was the true hero of reionization? Was it the short-lived brilliance of the first stars, the patient work of countless galaxies, or the focused power of quasars? The answer remains frustratingly out of reach because our most powerful telescopes are straining to see this far back in time. The light from these first sources is incredibly faint, stretched into the infrared by the expansion of the universe, and often obscured by the very fog they were trying to clear. It is a cosmic crime scene where the primary witnesses have long since vanished, leaving behind only the faintest echoes for us to decipher. Even the echoes of the first light carry a secret, a hidden timeline that scientists are desperate to decode. The second great mystery of the reionization era is its precise schedule. When exactly did the lights first flicker on across the cosmos? How long did this great transformation take? And when was the final patch of fog finally burned away? We have clues, but they paint a picture filled with uncertainty. One of our most powerful pieces of evidence comes from the cosmic microwave background, the ancient afterglow of the Big Bang itself. This faint light, which fills the entire universe, carries the scars of its journey through the reionizing gas. As the first ultraviolet light began to tear electrons away from atoms, it left a distinct imprint on this background radiation, a subtle polarization that our telescopes can detect. This tells us that reionization was largely complete by the time the universe was around 1 billion years old. But that is a very broad deadline. To get a more detailed schedule, we look to distant quasars. The light from these brilliant beacons travels billions of light years to reach us, and on its journey, it passes through clouds of neutral hydrogen. By studying the absorption lines in a quasar's spectrum, scientists can see how much of that fog was still present at different cosmic distances, which correspond to different times in the past. The evidence from quasars suggests reionization was a long and drawn-out process. It did not happen everywhere at once. Instead, it was likely a patchy and uneven transition. Imagine a dense forest at dawn. The first rays of sun do not illuminate the entire woodland instantly. They first create isolated, bright clearings that slowly grow and merge until the entire forest is bathed in light. The cosmos likely reionized in the same way, with brilliant bubbles of ionized gas expanding and eventually overlapping over hundreds of millions of years. But the exact start time, the moment of peak activity, and the final end date remain hotly debated. Was it a swift and violent revolution or a slow and patient erosion? The answer is written in the faintest light from the edge of time, a message we are only just learning how to read. But even the galaxies we can detect might not be the whole story. The third great mystery of reionization lies in the shadows, with the countless faint galaxies that our telescopes simply cannot see. What if the real work was done not by the brilliant giants, but by an unseen multitude of cosmic dwarfs? This is the puzzle of the faint galaxies, and it connects directly to a famous problem in astronomy known as the missing satellites problem. Our theories of how galaxies form predict that our own Milky Way should be surrounded by thousands of small, satellite dwarf galaxies. Yet we only see a few dozen. Where are all the rest? The leading idea is that they are there, but they are just too dim for our current instruments to pick up. This exact same principle applies to the early universe. If the cosmos is teeming with trillions of incredibly faint dwarf galaxies, each one leaking a tiny amount of ionizing radiation, their collective power could have been overwhelming. Imagine trying to heat a vast lake not with a few giant blowtorches, but with millions of tiny tea lights scattered across its surface. The combined warmth could be just as effective and might even provide a more uniform, steady heat. This is a compelling theory, but it remains just that, a theory, because we lack the proof. Finding these faint galaxies is one of the primary missions for new observatories like the James Webb Space Telescope. With its colossal mirror and infrared sensitivity, Webb is designed to peer deeper into the cosmic past than ever before, hunting for the faint, red glows of these elusive dwarf galaxies. If it finds them in vast numbers, it would completely reshape our understanding of the reionization era. We would have to rewrite the story, shifting the credit from a few cosmic celebrities to a silent, immense army of tiny contributors. The very fabric of the early universe might have been woven not by a handful of brilliant needles, but by a countless, faint tapestry of threads. Even if a galaxy was blazing with newborn stars, its light might never have reached the cosmic fog. This leads us to the fourth great mystery, a problem of cosmic escape. Scientists call it the escape fraction. It is the critical, unknown percentage of a galaxy's ionizing radiation that actually managed to break free. Inside every young galaxy, a fierce battle was being waged. Vast clouds of gas and dust, the very material from which stars are born, also acted as a prison for their most energetic light. Ultraviolet photons, the very particles needed to rip electrons from hydrogen atoms, would travel only a short distance before being absorbed by another gas atom, their energy lost. For reionization to work, this deadly light had to find a clear path out of its galactic home. The challenge was immense. Imagine a dense, smoky room filled with countless light bulbs. The smoke absorbs most of the light, leaving the room dim. Now picture a few narrow, clear chimneys suddenly opening to the outside. Only the light that happens to be pointing directly at those chimneys can escape to illuminate the world beyond. Early galaxies likely had similar structures, with channels carved by stellar winds or supernova explosions that allowed a precious fraction of their ionizing radiation to stream out into intergalactic space. But what was that fraction? Was it a meager 5% of the total light, or a more substantial 20% or even 50%? This single number is one of the most important and elusive values in all of cosmology. If the escape fraction was too low, then even a universe packed with galaxies could not have powered reionization. The fog would have remained. Measuring this value today is incredibly difficult. We are trying to observe the faint, specific signature of escaping ultraviolet light from galaxies that are at the very edge of our observational limits. The light is so faint and so stretched that it is often lost in the glare of the galaxy's own non-ionizing starlight, or absorbed by intergalactic hydrogen on its long journey to our telescopes. It is like trying to hear a single, specific whisper in a roaring stadium from miles away. Without knowing this crucial escape fraction, we cannot truly know if the galaxies we see were powerful enough to reshape the entire universe, or if we are still missing a fundamental piece of the puzzle. The cosmic fog did not lift like a single curtain falling. It evaporated in patches, creating a strange and uneven landscape across the young universe. This fifth mystery, the inhomogeneity of reionization, reveals that the dawn of light was a messy and fragmented affair. The evidence for this patchiness is written in the light of the most distant quasars we can observe. When astronomers analyze the spectra of these brilliant beacons, they do not see a clean, uniform absorption signal. Instead, they see a complex tapestry. Some lines of sight show clear stretches where the light passed through fully ionized space, while other paths, even those right next to each other, show the deep shadows of lingering neutral hydrogen. It is as if the quasar's light is shining through a vast cosmic Swiss cheese, with some holes punched all the way through and other regions still solid and opaque. This tells us that reionization was not a global flip of a switch. It was a process driven by local sources, creating isolated bubbles of clarity that slowly grew and merged. To understand how this could happen, scientists turn to sophisticated computer simulations. They create virtual universes inside supercomputers, seeding them with potential first light sources based on our best theories. They then let the simulation run, watching as the digital cosmos evolves. In these virtual realms, you can witness the birth of the first reionization bubbles. A massive galaxy or a brilliant quasar ignites at the center of a vast dark region. It begins flooding its surroundings with intense ultraviolet radiation, pushing back the fog and creating a growing sphere of ionized plasma. For a time, this bubble is an island of light in a sea of darkness. Then, another source ignites somewhere else, creating its own bubble. Over millions of years, these bubbles expand, their edges brushing against one another and finally merging into vast, connected ionized regions. The final patches of neutral hydrogen would have been the most isolated and stubborn, the cosmic equivalents of deep, shadowy valleys that saw the sun last. The very patchiness of this process is a crucial clue. It tells us that the first ionizing sources were not spread evenly throughout space like sprinkles on a cupcake. They were clustered, gathered in cosmic metropolises separated by vast, empty voids. This uneven distribution is exactly what we would expect from the way galaxies form, condensing at the intersections of the cosmic web of dark matter. The observed inhomogeneity is a powerful, indirect confirmation that the engines of reionization were indeed discrete objects like galaxies and quasars, and not some mysterious, uniform background energy. It forces us to picture the early universe not as a simple, homogeneous soup, but as a dynamic and complex place where the first great battle between light and darkness was fought neighborhood by neighborhood. Yet the patchiness of the cosmic dawn points directly to sources of unimaginable power. The sixth mystery confronts us with the universe's most violent and brilliant engines, the quasars and their kin active galactic nuclei. Could these cosmic monsters, fueled by ravenous supermassive black holes, have been the primary architects of reionization? The case for them is both simple and terrifying. A single quasar can outshine an entire galaxy of stars, unleashing a torrent of ultraviolet and X-ray radiation so intense it can ionize hydrogen for millions of light years in every direction. Think of it not as a light bulb, but as a celestial blowtorch, capable of sterilizing vast volumes of space and carving out the largest bubbles in the reionizing foam. Their focused power seems like the perfect tool for such a monumental task, but the case against them is equally compelling, rooted in a simple question of numbers. Quasars are incredibly rare. For every one of these brilliant beacons, there were likely millions of ordinary star-forming galaxies. Could a handful of blowtorches, no matter how powerful, really have heated the entire cosmic ocean, or would their effect have been more like poking a few brilliant, isolated holes in the fog? The evidence we have from deep sky surveys suggests the latter. When we look back to the epoch of reionization, we find very few quasars. Their golden age seems to have come slightly later, after the cosmic fog had largely cleared. This timeline is a major strike against them being the dominant force. Furthermore, the very nature of their radiation might have been a double-edged sword. The intense X-rays from quasars can penetrate much deeper into clouds of neutral hydrogen than ultraviolet light can. Instead of immediately ripping electrons away, these X-rays would have heated the gas, making it harder for it to clump together and form new stars. In some scenarios, a quasar might have actually suppressed star formation in its vicinity, potentially choking off the very sources that could have continued the reionization work. So were they heroes or villains in this cosmic drama? The most likely answer is that they played a crucial but supporting role. They were the special forces of reionization deployed to the densest regions of the cosmic web. There, their unmatched ferocity could punch through the toughest pockets of resistance, creating the initial bubbles that allowed the slower, steadier light from countless smaller galaxies to seep in and finish the job. Their contribution remains one of the great balancing acts in cosmology, a question of whether sheer, concentrated power can ever truly outweigh the patient work of the multitude. The same radiation that tore the universe from its slumber did more than just illuminate the void. It also turned up the heat, transforming the cosmic environment in a way that would dictate the future of galaxy formation for billions of years. This is the seventh mystery, the profound and lingering question of the intergalactic medium's temperature. The vast, near-empty spaces between galaxies are not a perfect cold vacuum. They are filled with an incredibly thin, superheated plasma, a ghostly gas that was warmed to temperatures of tens of thousands of degrees during the reionization era. But how did this heating happen, and why does its precise history remain so elusive? When an energetic ultraviolet photon strikes a neutral hydrogen atom, it does not just liberate an electron. That collision also transfers energy, effectively giving the newly freed electron a kick, like a cue ball striking another on a pool table. These hot electrons whizzing through space collide with other particles, spreading their kinetic energy and raising the overall temperature of the entire gas. This means the reionization process was not just a light show, it was a cosmic oven slowly baking the intergalactic medium. The puzzle for scientists is determining the exact temperature this gas reached and, more importantly, how that temperature changed over time. Was it a sudden, violent blast of heat or a slow, steady warming? The answer is written in the subtle absorption lines found in the spectra of distant quasars. As a quasar's light journeys to us, it passes through countless filaments of this intergalactic gas. The gas imprints a unique fingerprint on the light, a forest of absorption lines known as the Lyman alpha forest. The width and shape of these lines are exquisitely sensitive to the temperature of the gas that created them. By analyzing this forest, astronomers can effectively take the universe's temperature at different points in its history. The data reveals a complex thermal story. The initial heating from the first starlight was likely intense, but the gas would have begun to cool almost immediately as the universe expanded. The real mystery involves potential later heating events. Did quasars, with their powerful X-ray emissions, pump additional energy into the system, creating a second, more sustained wave of heat? This temperature history is not just a trivial detail. It is a fundamental parameter that governed the next chapter of cosmic evolution. a hotter intergalactic medium is more resistant to collapse. Think of it like trying to form a snowball with warm, slushy snow versus hard, packed, cold snow. If the gas between galaxies remained too hot for too long, it would have made it much more difficult for small, new galaxies to form, especially the faint dwarf galaxies we discussed earlier. This heating effect could have essentially put a brake on the formation of smaller cosmic structures, favoring instead the growth of only the largest, most massive galaxies. The temperature of this primordial gas, set over 13 billion years ago, may have dictated the very architecture of the cosmic web we see today. Unlocking its precise history is like finding the faded recipe for the universe itself, a set of instructions that determined how everything we see could eventually take shape. These first stars have left behind a ghostly fingerprint, a chemical legacy written in the oldest stars we can actually see. The hunt for population 3 stars is not just about catching their light, it is about reading the story they etched into the cosmos when they died. Because these titans lived fast and died young, they forged the universe's first heavy elements in their cores and in their violent supernova deaths. They were the original cosmic alchemists, transforming pristine hydrogen and helium into the first sprinklings of carbon, oxygen, and iron. When they exploded, they seeded the surrounding gas clouds with these new, heavier atoms. The next generation of stars, population 2 stars, then formed from this slightly enriched material. We have observed many of these ancient population 2 stars in our own galactic neighborhood. By analyzing their light with a technique called spectroscopy, astronomers can read their chemical composition like a recipe, and that recipe is startlingly simple. They contain only trace amounts of elements heavier than helium, what astronomers call metals. This pristine quality is the telltale sign that they formed from gas that was only lightly seasoned by a single prior generation of stars, the legendary population 3. So we see the shadow of those first giants in the profound emptiness of their children's chemical makeup. The direct observational challenge is immense. A single population 3 star would be an island of pure hydrogen and helium, a composition that does not exist anywhere in the nearby universe. Its light would have a unique and unmistakable signature, completely devoid of those metal lines we see in every other star. Finding such a star would be the ultimate cosmic prize, but these stars are so far away, their light stretched and faded by 13 billion years of cosmic expansion, that they are almost certainly beyond the direct view of even our most powerful telescopes. They are like mythical creatures whose existence we infer only from the unique footprints they left in the cosmic mud. The James Webb Space Telescope is our best hope for finally glimpsing them, not as individual points of light, but perhaps as the combined glow of entire clusters in the most distant galaxies. It is a search for a ghost using the most advanced machinery humanity has ever built, all to confirm the existence of the very first sunrise. That heat left a permanent scar on the cosmic landscape. The intense radiation that cleared the fog did more than just illuminate the void. It actively began to shape the future architecture of the universe itself. This is the 9th mystery, a powerful feedback loop where the very process of reionization began to dictate which galaxies could form and which were doomed to fail. The primary victims of this cosmic upheaval were the smallest, most fragile structures, the dwarf galaxies. To understand why, picture a small cloud of gas trying to collapse under its own gravity to form a new galaxy. This process requires the gas to cool down, allowing atoms to clump together. Now, imagine that same cloud is suddenly bathed in the intense ultraviolet light from the reionizing universe. This radiation heats the gas, giving its atoms so much energy that they resist collapsing. For a large, massive galaxy with a strong gravitational pull, this external heating is a minor nuisance, like a gentle breeze against a boulder. But for a tiny proto-galaxy, a mere wisp of gas, it is a hurricane. The heat provides enough pressure to overcome the cloud's weak gravity, preventing it from ever collapsing. The gas is effectively sterilized, scattered back into the intergalactic medium, its potential for star formation forever lost. This process created a kind of cosmic minimum wage for galaxy formation. Only clouds above a certain mass threshold, with gravity strong enough to fight back against the universal heating, could successfully form stars and become galaxies. This is a compelling explanation for the missing satellites problem we encountered earlier. The theories predict thousands of small dwarfs around our Milky Way, but we see only a few. Reionization provides the grim answer. It appears that most of these small galaxies were strangled in their cradle, never given a chance to grow. So the reionization era was not a passive event, it was an active sculptor. By systematically suppressing the formation of the smallest galaxies, it ensured that the future of the cosmos would be dominated by larger, grander structures. The universe, in its violent adolescence, set the rules for its own maturity, creating a galactic hierarchy that we still observe billions of years later. The cosmic dawn was not just a birth of light, it was a ruthless act of cosmic curation. The ghost of the cosmic fog still haunts the light traveling to us across the eons. We can read its story in one of the most beautiful and complex phenomena in all of astronomy, the Lyman Alpha Forest. This is not a place of trees, but a forest of shadows, a spectral fingerprint etched into the light of distant quasars. When a quasar's brilliant beam journeys for billions of years to reach our telescopes, it passes through countless filaments and clouds of neutral hydrogen that still linger in intergalactic space. Each cloud acts like a filter, absorbing a very specific shade of ultraviolet light known as the Lyman alpha line. The result is a stunning barcode of absorption lines, a dense thicket of dark spikes in the quasar's rainbow spectrum. Each spike is a shadow cast by a single cloud of hydrogen, a fossil relic from a specific moment in cosmic history. The structure of this forest is a direct record of the state of the universe when the light passed through it. Before reionization began, the universe was filled with a smooth, dense sea of neutral hydrogen. Any quasar light from that time would show a single, deep and continuous absorption trough, a total blackout of certain wavelengths with no forest of individual lines. This feature, called the Gunn-Peterson trough, is the ultimate signature of a universe still shrouded in pristine fog. As reionization progresses, the picture changes dramatically. The intense ultraviolet light begins to break apart the hydrogen atoms, but not uniformly. The process is patchy, leaving behind a complex web of ionized bubbles and lingering neutral regions. The quasar light now encounters a chaotic mix of clear passages and dense clouds. Its spectrum transforms from a single trough into a sparse collection of deep, black absorption lines. These are the shadows of the last great neutral hydrogen clouds, the stubborn holdouts against the advancing light. Once reionization is complete, the universe is a different place. The intergalactic medium is now a hot, thin, and highly ionized plasma, but it is not perfectly smooth. The gravitational pull of the cosmic web, the vast structure of dark matter that underpins the universe, has gathered much of the remaining gas into an intricate network of filaments and sheets. A quasar's light now travels through this evolved cosmic environment. It passes through these diffuse filaments, each one creating a much shallower, finer absorption line in the spectrum. The result is the dense, fine-grained Lyman alpha forest we see from quasars in the more recent universe. By studying the evolution of this forest, from a total blackout to a sparse collection of deep lines and finally to a dense, fine-grained tapestry, astronomers can piece together a precise timeline of reionization. They can determine when the fog was thickest, when it began to clear, and when the last patches finally evaporated. The Lyman alpha forest is more than just a fossil. It is a living chronicle of the universe's most dramatic transformation, a billion-year story written in shadows and light. That stellar archaeology provides our only tangible link to the universe's first generation of stars. Scattered throughout our own Milky Way are ancient suns, relics nearly as old as the cosmos itself, that hold chemical secrets locked within their light. By dissecting that light with spectroscopy, astronomers act as cosmic historians, reading the elemental abundances of these ancient stars to understand the environments in which they were born. The story they tell is a strange one. Many of these primordial stars show a bizarre chemical signature, an extreme abundance of elements like carbon and oxygen, yet a near-total absence of heavier metals like iron. This peculiar pattern is the crucial clue. It points directly to the explosive deaths of the first stars, the population 3 giants. When one of these behemoths reached the end of its short life, it did not die in a typical supernova. Instead, it may have undergone a pair instability supernova, a cataclysm of such unimaginable force that the entire star is obliterated, leaving no remnant black hole or neutron star behind. In this total self-destruction, the star's internal layers are blasted out into space, but the fusion process is cut short before it can create significant amounts of iron. The result is a cloud of gas rich in lighter elements from carbon to silicon, but strikingly poor in iron. The next generation of stars, the ones we see today as ancient fossils, then formed from this selectively enriched material. They inherited this specific chemical fingerprint, a cosmic DNA that reveals the nature of their colossal, long-vanished parents. Finding a star with virtually no iron, but a surprising amount of carbon, is like finding a fossilized bone with the tooth marks of a predator we have never seen. It tells us not only that the predator existed, but also how it hunted and what it consumed. This stellar archaeology is a painstaking search for the rarest of treasures, the few surviving stars that carry the pure, unaltered signature of a single population 3 supernova. Each one found is a time capsule, a direct messenger from the era of the first dawn, confirming that the universe's pioneers were indeed monsters whose violent death set the stage for everything to come. Deep within the silent sea of neutral hydrogen, there is a whisper. Every atom of this primordial gas holds the potential to broadcast a very specific radio signal, a faint pulse with a wavelength of 21 centimeters. This whisper is now the focus of an astronomical hunt that could one day provide a perfect 3-dimensional movie of the cosmic dawn. The promise is breathtaking. Because neutral hydrogen existed everywhere before reionization, mapping this 21-centimeter signal across the sky and back through time would let us watch the fog lift in real time in 3 dimensions. We would see the first ionized bubbles flicker into existence, trace their growth as they merged, and witness the final stubborn patches of darkness dissolve. It would be the ultimate timeline, a direct observation of the universe's great transformation. The challenge, however, is almost beyond comprehension. This signal is incredibly faint, having traveled for over 13 billion years. Its wavelength has been stretched by the expansion of the universe from 21 centimeters to many meters, placing it in the long-wave radio part of the spectrum. And here on Earth, this part of the radio dial is flooded with deafening noise. Every FM radio station, every television broadcast, every satellite transmission, and even the natural radio emissions from our own galaxy create a roaring static that is millions of times louder than the cosmic whisper we are trying to hear. Separating the signal from this interference is like trying to hear the flutter of a butterfly's wings from inside the engine room of a jet plane. To overcome this, radio astronomers are building vast, silent ears in some of the most remote locations on Earth. Projects like the Hydrogen Epoch of Reionization Array in South Africa and the Future Square Kilometre Array in Australia and South Africa use fields of simple radio antennas spread across miles of desert. Their strategy is not to build one giant dish, but to create a massive digital telescope by combining the signals from thousands of small ones. By carefully comparing the subtle differences in the signal received by each antenna, supercomputers can slowly and painstakingly filter out the foreground roar of modern civilization and our own galaxy. attempting to isolate the pristine hum of the ancient hydrogen. The data they seek is not a pretty picture, but a subtle statistical fluctuation in the radio noise. Finding that specific pattern is an act of immense patience and computational power. Success would mean unlocking a direct window into the Dark Ages, allowing us to see the structures of the early universe not with light, but with the shadowy radio glow of the very gas that was being destroyed. It is a gamble of technology and intellect against the faintest echo in the cosmos, all for a chance to witness the dawn. That transformation from a foggy sea to a clear expanse created a new cosmic reality, one defined by transparency. The 13th mystery asks a profound question: why did the universe, after being so stubbornly opaque, suddenly become a window to the depths of space? The answer lies in a fundamental shift in the very nature of the intergalactic medium. Before reionization, space was filled with neutral hydrogen atoms. These atoms are incredibly efficient at capturing and scattering a specific, high-energy form of ultraviolet light. Any photon of this particular wavelength trying to travel through that ancient fog would be quickly absorbed, its journey cut short after just a short distance. It was like trying to see through a dense, white-out blizzard where every snowflake blocks your view. But when the first starlight and quasar radiation began to flood the cosmos, it ripped electrons away from their atomic homes. This changed everything. A sea of neutral atoms became a diffuse soup of free electrons and bare protons. This ionized plasma is remarkably transparent to that same ultraviolet light. The freed electrons are simply too small and spread out to effectively catch the photons anymore. The once impenetrable blizzard had vanished, replaced by a clear, dark sky. This transition in opacity had a direct and dramatic effect on the light we can now observe. The most energetic light from the earliest galaxies and quasars, the very light that did the work of reionization, was once trapped. Now it could travel freely across the cosmos. This is why our most powerful telescopes can, in principle, see these ancient objects. The universe cleared a path for their story to be told. But this transparency came with a cosmic trade-off. While the universe became clear for high-energy ultraviolet light, it remained stubbornly opaque for a different kind of radiation, the low-frequency radio waves from the neutral hydrogen itself. The very process that allowed us to see the first stars also silenced the primordial hum of the gas that once filled the darkness. We gained a view of the brilliant new cities of light, but we lost the ability to hear the quiet whisper of the empty land they were built upon. This shift in cosmic opacity is the final, permanent legacy of reionization. It fundamentally altered the channels through which the universe communicates with us, choosing which messages from the dawn of time would survive the 13-billion-year journey to our telescopes and which would be lost forever to the silence of the past. But the brilliant bubbles of light did not form randomly in the void. They were guided by an unseen hand, a cosmic architect whose presence we can only infer from its immense gravitational pull. This 14th mystery pulls back the curtain on the true stage for reionization, the invisible scaffolding of dark matter. Though dark matter itself does not emit, absorb, or scatter light, its role was absolutely fundamental. It provided the gravitational wells, the deep pits in the fabric of space, where the ordinary gas of hydrogen and helium could collect, grow dense, and eventually ignite into the first stars and galaxies. Without this dark framework, the universe might have remained a formless, dark sea forever. The very nature of this dark matter, however, could have dramatically altered the story of cosmic dawn. The leading model, known as cold dark matter, posits that these particles are slow-moving and only interact through gravity. In this scenario, dark matter clumps efficiently from the bottom up, creating a vast cosmic web of tiny halos that then merge into larger structures. This bottom-up growth would have seeded a universe teeming with countless small, faint galaxies early on, potentially kick-starting reionization in a slow and steady manner. But what if dark matter is not so simple? Alternative models like warm dark matter propose particles that were moving much faster in the early universe. This extra motion would have smoothed out the smallest clumps, acting like a cosmic breeze that prevents the tiniest dust bunnies from forming. In a warm dark matter universe, the first galaxies to form would have been larger and more massive, but also much rarer. Reionization in this scenario would have begun later, as it took more time for these fewer, larger galaxies to accumulate enough gas. The process might have been more abrupt, with powerful but isolated bubbles suddenly piercing the gloom. An even more exotic idea is self-interacting dark matter, where the invisible particles can actually collide and scatter off one another, much like molecules in a gas. This interaction would tend to smooth out the dense cores of dark matter halos, making them puffier. This could have profound consequences for the first stars and galaxies forming within them. A puffier halo might hold onto its gas less tightly, potentially making it easier for the intense radiation from the first stars to blow that gas away, effectively shutting down further star formation in that small halo. This could have throttled the contribution of the smallest galaxies, shifting the burden of reionization onto larger, rarer systems. The specific flavor of dark matter, a substance that makes up over 80% of the universe's mass, would have written the rules for the reionization game. It determined the size of the first playing pieces, the timing of the first moves, and the overall strategy of light's victory over darkness. Unlocking the true identity of dark matter is not just a quest for fundamental physics. It is the key to understanding why our cosmic dawn unfolded the way it did, and why we are here to see its lingering glow at all. Even the universe's greatest transformation had to end, but pinpointing that final moment, the precise instant the cosmic fog fully lifted, remains one of the most stubborn puzzles of the reionization era. When exactly did the universe declare itself transparent once more? The challenge is that this ending was almost certainly not a single dramatic event. It was not like a final light switch being flipped, illuminating every last corner of space. Instead, it was a gradual fading, a long, drawn-out tale where the last vestiges of neutral hydrogen were slowly burned away. Astronomers cannot simply point to a date in cosmic history and say, "Here, this is when it was over." Instead, they rely on a series of observational thresholds, each one telling a different part of the story. One crucial piece of evidence comes from the spectra of the most distant quasars. When we look at quasars from a time just after reionization is thought to have ended, we no longer see the complete Gunn-Peterson trough, that signature of a fully neutral universe. But we do see something else, a sparse collection of the very deepest absorption lines in the Lyman alpha forest. These are not the fine, wispy lines from the diffuse cosmic web, but dark, profound shadows. Each one represents a final, dense cloud of pristine hydrogen, a lone island of fog that managed to survive the advancing light. The end of reionization, then, is marked by the disappearance of these last great holdouts. It is the moment when the quasar spectra show no more of these deep, black absorption lines, leaving only the finer, more uniform forest created by the ionized filaments of the cosmic web. Another threshold involves the cosmic microwave background. The polarization imprint left on this ancient light gives us a volume-averaged measurement. It tells us what percentage of the universe was ionized at a given time. Declaring the era over requires agreeing on a specific number, a percentage of neutral hydrogen so small that it is considered negligible. But what is that number? Is it when 99.9% of the hydrogen is ionized, or is 99% enough? The difference might seem trivial, but in a cosmos as vast as ours, that last 0.1% could represent an immense amount of neutral gas, clinging to existence in the most isolated cosmic voids. This final cleanup might have taken an astonishingly long time, perhaps hundreds of millions of years after the main event was technically over, so the end of reionization is a blurry finish line. We know the race was largely run by the time the universe was around 1 billion years old, but the final stragglers were still crossing long after. The universe did not become perfectly, absolutely transparent. It simply became transparent enough for its brilliant new galaxies to finally shine across the ages without being completely smothered. The end was not a moment, but a fading whisper, the last echo of the dark ages dissolving into the clear, star-filled silence we know today. Even the faintest light from the Big Bang holds a frozen memory of that great awakening. Etched into the cosmic microwave background are subtle swirls and patterns, a polarization that tells the story of the reionization era's final act. When the first starlight ripped electrons from their atoms, it created a universe filled with free electrons, tiny particles now drifting through the newly transparent space. As the ancient CMB light, already billions of years old, journeyed through this charged environment, its photons would occasionally bounce off these free electrons. This scattering process, much like sunlight glinting off the surface of a lake, imprinted a specific kind of order onto the light's orientation, polarizing it. This polarization comes in two distinct flavors, known to astronomers as E modes and B modes. The E mode pattern is relatively gentle, a curling, curl-free signature that arises from the density fluctuations in the early universe, amplified by the scattering during reionization. It is the primary fingerprint we have detected, and it gives us a crucial, broad brush timeline. The strength of this E-mode signal tells us roughly how many electrons those CMB photons encountered on average. This allows cosmologists to estimate the total amount of scattering that occurred, which in turn tells us when most of the reionization process was complete. It is like hearing the echo in a vast hall. The strength of the echo tells you something about the size of the room and when the sound was made. But the real cosmic grail, the signal that could reveal even more dramatic secrets, is the B mode. This pattern is a spiraling, twisting signature, a potential relic of primordial gravitational waves rippling through the fabric of space-time from the universe's first violent moments. Detecting a primordial B-mode signal would be one of the greatest discoveries in all of science. Yet, for the story of reionization, even the faintest hint of B-modes created by later processes helps us understand the energy involved. The specific polarization patterns we see confirm that reionization was not an instantaneous flash. The data aligns with a drawn-out process, a protracted dawn where bubbles of ionized gas grew and merged over several 100 million years. It tells us that the total energy output from those first stars and galaxies was immense, but it was delivered not as a single, shattering blast, but as a sustained cosmic campaign. This ancient polarization is a final, all-sky monument to the era, a frozen record of the moment the universe's fundamental nature changed, and its deepest patterns are still being decoded. This same cosmic feedback loop may be the key to a modern galactic mystery, the missing satellites problem. Our best models of the cosmos predict that a galaxy like the Milky Way should be surrounded by a vast swarm of tiny satellite dwarf galaxies, perhaps thousands of them. Yet when we look, we find only a few dozen. Where are all the rest? The answer might lie in the harsh environment created by reionization itself. Think of the countless small clouds of gas that existed in the early universe, each one a potential cradle for a future dwarf galaxy. They were the smallest, most vulnerable structures. When the cosmic ultraviolet background light flooded the universe, it bathed these fragile clouds in a sterilizing radiation. The gas inside them was heated, and for a cloud with very weak gravity, that heat provided enough outward pressure to overcome its inward pull. It was like a gentle but constant wind blowing against a dandelion seed, preventing it from ever landing and taking root. These small halos of dark matter were left permanently barren, ghosts with the potential for stars but never the chance to ignite. They are still out there, invisible dark matter skeletons, but they failed to light up and become the galaxies our theories predicted. This cosmic suppression created a minimum mass for galaxy formation. Only the clouds that were massive enough, with gravity strong enough to withstand the universal heat, could collapse and form stars. The satellites we do see around the Milky Way are the lucky survivors, the ones that were just large enough to fight back. The rest were effectively strangled in their cradle over 13 billion years ago, their starlight extinguished before it could even begin to shine. So the quiet, empty halo of our own galaxy today may be the direct and lasting legacy of that first violent dawn, a permanent scar from the era when light itself decided which galactic seeds would be allowed to grow. These supermassive black holes appeared impossibly early, challenging our very understanding of cosmic time. How could objects with the mass of 1 billion suns form in less than 1 billion years? Their existence at the dawn of the Reionization era presents a monumental timing problem. If they grew from the remnants of the first massive stars, it would have taken far too long. A stellar mass black hole would need to consume gas at a breakneck, unsustainable pace for its entire life to reach such colossal sizes so quickly. The math simply does not add up. This paradox points toward a far more exotic and dramatic birth, one uniquely suited to the strange conditions of the early universe. Astronomers call this the direct collapse model. Picture a pristine cloud of primordial gas in the early cosmos, a vast and silent reservoir of hydrogen and helium. Under normal circumstances, such a cloud would fragment, collapsing into countless clumps that ignite as a cluster of stars. But in the peculiar environment of the Reionization era, a different fate was possible. If a nearby galaxy or a population of hot stars began flooding this cloud with intense ultraviolet radiation, it could fundamentally alter the cloud's chemistry. This radiation would prevent the gas from cooling efficiently by breaking apart the hydrogen molecules that allow heat to escape. The cloud, unable to shed its thermal energy, could not fragment. It would remain a single, monstrously large and stable mass. Then, under its own immense weight, it would undergo a catastrophic, wholesale collapse. There would be no twinkling of new stars, no stellar nursery. Instead, the entire vast cloud would plunge directly into a gravitational abyss, forging a supermassive black hole seed in one single cosmic event. This seed, already thousands of times more massive than any star, would have a tremendous head start. Its powerful gravity could then pull in surrounding gas with terrifying efficiency, rapidly growing into the quasar-powering behemoths we detect in the young universe. This process offers a compelling solution, but it hinges on very specific and likely rare conditions. The parent gas cloud had to be massive, pristine, and bathed in just the right amount of external radiation. Too little radiation and the cloud fragments into stars. Too much and the gas is blown apart entirely. It was a cosmic tightrope walk, a fleeting window of opportunity during the Reionization era that allowed these monsters to be born. The existence of these early quasars is therefore not just a mystery, but a direct clue. It tells us that the universe's first light did more than just clear a fog. It actively forged the darkest and most powerful engines at the heart of the nascent cosmic web. Hydrogen was not the only element waiting for its moment of liberation. Lurking within the cosmic plasma was another, more stubborn prisoner, helium. The ionization of hydrogen was only the first act in a two-part cosmic drama. The universe had to undergo a second, even more violent upheaval to fully assert its transparency, a later chapter known as helium reionization. While hydrogen's electron is bound with a certain energy, helium clings to its last electron with a ferocious grip, requiring photons of much higher energy to break it free. The gentle starlight that cleared the hydrogen fog was useless against this tougher atomic fortress. Only the most extreme objects in the cosmos could produce the hard ultraviolet and even soft X-ray radiation needed for this task. The prime suspects are once again the quasars. Their accretion disks swirling around supermassive black holes become unimaginably hot, blazing with the energy to produce the precise photons that could strip helium atoms bare. This second ionization did not happen until the universe was perhaps 2 or 3 billion years old, a full 1 to 2 billion years after the hydrogen fog had lifted. It was a delayed and distinct event powered by a different cast of cosmic characters. The effect of this second ionization was not just about light, it was about heat. Just as with hydrogen, each liberated electron carried away a kick of energy, but this time the kick was far more powerful. The photons that ionized helium were so energetic that they transferred a tremendous amount of heat into the already warm intergalactic medium. This event likely reheated the cosmos to even higher temperatures, injecting a fresh wave of thermal energy that counteracted the natural cooling from the universe's ongoing expansion. This second heating episode adds a profound layer of complexity to the thermal history of the universe. The intergalactic medium did not simply heat up once and then steadily cool down. Its temperature chart would show a dramatic spike during hydrogen reionization, a slow decline, and then another significant spike during the helium era. This thermal roller coaster had real consequences. It further influenced how and where gas could collapse to form new generations of galaxies, potentially altering the growth of the cosmic web during a more mature phase of universal history. The story of reionization is not a single explosion of light, but a double-barreled event, a 1-2 punch that first cleared the fog and then supercharged the emptiness, ultimately shaping the transparent, complex universe we observe today. Before a single star could ignite, the universe had to learn how to build. The formation of the very first molecules was the critical, invisible step that made all future light possible. This period, the cosmic dawn, was a time of profound chemical transformation, a quiet overture before the stellar symphony began. The protagonist of this prelude was a simple diatomic molecule, molecular hydrogen. In the aftermath of the Big Bang, the universe was a hot soup of atomic nuclei and free electrons. As it expanded and cooled, these particles combined to form neutral hydrogen and helium atoms. But this atomic gas had a problem. It was too hot to collapse under its own gravity. To form a star, a cloud of gas must be able to cool down, radiating away its thermal energy so that gravity can win the battle and cause the cloud to condense. Single atoms are notoriously inefficient at this cooling process. They are like single bricks that cannot be used to build a house. Molecular hydrogen, however, was different. When two hydrogen atoms joined together, they created a structure that could vibrate and rotate in specific ways. These motions allowed the molecule to emit radiation, effectively acting as a miniature radiator that could carry heat away from the gas cloud. This molecular cooling was the universe's first air conditioning system, and it was absolutely essential. It allowed the dense, dark cores of these primordial gas clouds to shed their heat, grow cold, and finally succumb to gravity's relentless pull, triggering the collapse that would birth the first protostars. Observing this epoch is a monumental challenge. The light from these first molecules is incredibly faint, and its wavelength has been stretched by cosmic expansion into the far infrared and radio bands, where our atmosphere itself creates a noisy, opaque barrier. We are trying to detect the ghost of a whisper from the edge of time. The most promising method involves hunting for a specific spectral line from molecular hydrogen, but this signal is drowned out by a cacophony of foreground emissions from our own galaxy and the modern universe. It is like trying to hear the first, faint note of a violin from an orchestra that has been playing for billions of years. The quest to witness the cosmic dawn is a push against the ultimate limits of observation, a search for the moment the darkness first learned how to create the tools for its own destruction. Our most powerful supercomputers have built entire virtual universes, and yet they still struggle to recreate the dawn of light. This is the 21st mystery, the growing gap between simulation and observation. Inside these digital realms, physicists program every known law of the universe. They set the initial conditions from the cosmic microwave background, sprinkle in dark matter according to our best models, and let gravity work its magic over billions of virtual years. The goal is to run this cosmic simulation and end up with a universe that looks exactly like the one we see today, complete with a reionization era that matches the faint clues from our telescopes. But there is a persistent tension. The simulations often require very specific and sometimes extreme parameters to produce the reionization we think we observe. For instance, to make the process happen early enough, the models might need an unrealistically high number of ultraviolet photons escaping from every single early galaxy. Or to create the large ionized bubbles we detect, the simulations might need to place quasars in places where we have no observational evidence for them. It is like trying to tune a complex engine by only listening to its hum from a mile away. You can twist the knobs to make the hum sound right, but that does not mean the engine inside is actually configured correctly. This gap tells us that our models are likely missing a crucial piece of physics. Perhaps the first stars were even more efficient at producing ionizing radiation than we think. Maybe there is an entire population of faint, unseen objects doing the work, or the dark matter could be behaving in a way we have not yet accounted for, changing how the first structures formed. Every time a simulation fails to match the data without being forced, it is not a failure of the computer, it is a success for discovery. It highlights a crack in our understanding, a place where the real universe is trying to tell us that something in our grand cosmic story is not quite right. This tension is the engine of scientific progress, pushing us to look deeper, to build better telescopes, and to question our most fundamental assumptions about the first chapters of cosmic history. A silent revolution is unfolding in the void, as a golden eye now peers deeper into the cosmic past than ever before. The James Webb Space Telescope is not just another observatory, it is a time machine specifically engineered to hunt for the dawn. Its mission is to confront the great mysteries of reionization head-on, transforming our faint whispers of understanding into a clear story. The telescope's greatest weapon is its profound sensitivity to infrared light. The expansion of the universe has stretched the ancient light from the first stars and galaxies far into the infrared part of the spectrum, a domain where Hubble was nearly blind. Webb sees this redshifted light with breathtaking clarity, allowing it to look back to within a few 100 million years of the Big Bang itself. One of its primary quests is to conduct a cosmic census of the earliest galaxies. By taking deep field images of the void, it is counting these faint red smudges, determining if there were truly enough galaxies to power reionization. Is the universe filled with a multitude of tiny, faint dwarfs, as some theories suggest, or were the brilliant giants the true heroes? Webb is not just counting them, it is also dissecting their light. Using its powerful spectrographs, the telescope can break apart the glow of a primordial galaxy into its constituent colors. Within that rainbow, it searches for the specific, telltale signs of intense ultraviolet radiation, the kind that can rip electrons from hydrogen. This allows scientists to directly measure the ionizing output of these early systems, moving beyond theoretical guesses to hard data. Perhaps the most tantalizing goal is the search for the mythical population 3 stars. Webb may not see them as individual points of light, but it could detect their collective signature. If an early galaxy shows a spectrum completely devoid of any heavy elements, it would be the smoking gun, evidence that its light is dominated by that first generation of pure hydrogen and helium giants. Every image from Webb is a new piece of evidence in this billion-year-old case, bringing us closer than ever to identifying the prime movers behind the universe's greatest awakening. This faint radio whisper from the dawn of time will not remain hidden forever. A new generation of colossal radio telescopes is being built with one primary mission: to transform that faint statistical hum into a detailed, three-dimensional movie of the universe's awakening. The most ambitious of these projects is the Square Kilometre Array, a monumental instrument now under construction across remote deserts in South Africa and Australia. Its name is not an exaggeration. When complete, it will form a collective radio receiving area of approximately 1 square kilometer, using thousands of individual antenna dishes and up to 1 million simpler dipole antennas. This vast digital ear is designed to listen to the universe on the long, stretched wavelengths of the ancient hydrogen signal. The goal is nothing short of revolutionary. Instead of inferring the history of reionization from a handful of distant quasars, the square-kilometer array aims to map the distribution of neutral hydrogen directly across the entire sky and back through billions of years of cosmic time. It will not provide a single static snapshot. It will produce a dynamic timeline, allowing us to watch as the first ionized bubbles flicker into existence, grow, and merge. We will witness the cosmic web of dark matter light up with the radio glow of hydrogen, only to see that glow vanish as the advancing wave of starlight burns it away. It would be like watching a time lapse of a foggy landscape at dawn, seeing exactly where the first rays of sun break through and how they slowly consume the shadows. The technical challenges are staggering. To isolate the cosmic signal, the telescope must peer through a cacophony of radio noise from our own galaxy, terrestrial interference, and the subtle distortions of Earth's atmosphere. The data output will be measured in petabits per second, requiring supercomputers more powerful than any that exist today to process the information. Success will depend on a symphony of engineering and computing, all working in perfect harmony to filter out the roar of the modern universe and amplify the faintest whisper from its infancy. If it succeeds, the square-kilometer array will do more than just solve the mysteries of reionization. It will open an entirely new window onto the Dark Ages, a period currently hidden from our view, revealing the very first structures that ever began to form in the cosmos. The pioneering galaxies that lit up the cosmos faced two starkly different destinies. Some were destined for glory, while others faded into cosmic obscurity. The ultimate fate of these first galactic pioneers is a story written in the silent archaeology of the present-day universe. The grandest of these early structures likely did not remain isolated islands for long. Their immense gravitational pull would have drawn in smaller neighbors, triggering a violent and relentless dance of mergers and acquisitions. Picture a bustling cosmic city, its gravity acting as a powerful magnet for smaller galactic towns. Over billions of years, these collisions and mergers would have built up vast, majestic structures, the giant elliptical and spiral galaxies we see today, like our own Milky Way. The brilliant core of a long-dead quasar, a key player in reionization, might now lie dormant as the supermassive black hole at the center of a modern galactic titan. Their legacy is the starlight of 1 trillion suns, yet for every one of these successful giants, there were likely countless smaller, fainter galaxies that followed a much quieter path. These cosmic dwarfs, perhaps the true unsung heroes of reionization, may have simply burned out after that first furious burst of star formation exhausted their limited gas reserves. They had nothing left to fuel a second act. They became galactic dead ends, their stellar populations aging into a faint, red glow before slowly fading from view over eons. Another, more violent fate was also possible. When venturing too close to a larger galaxy, their delicate structures would have been shredded by overwhelming tidal forces, their stars stripped away and assimilated into the halo of the giant. They became galactic ghosts, their identity erased, their contributions dissolved into the anonymous glow of a larger galaxy's faint outer reaches. So when we look at the Andromeda Galaxy or the majestic Sombrero, we may be looking at the consolidated remains of thousands of those first pioneers, their light and history forever merged. And when we detect a faint red smudge at the edge of our observations, we might be witnessing the final, dying ember of a galaxy that once helped to illuminate the entire universe, a silent testament to a dawn it helped create. This final mystery stares into the deep future and asks a haunting question. Could the cosmic dawn ever be reversed? Is there a scenario where the universe, now a transparent expanse, could plunge back into a neutral fog, entering a second dark age? The answer lies in the delicate balance between the sources of ionizing radiation and the universe's own relentless expansion. For reionization to happen again, the intergalactic medium would need to somehow become neutral once more. This requires the number of free electrons and protons to find each other and peacefully recombine into neutral hydrogen atoms, a process that demands a much colder and denser environment than the one we have today. Right now, the cosmos is kept ionized by a steady background of ultraviolet light from countless active galaxies and quasars, but the universe is changing. As expansion continues to accelerate, driven by the mysterious force of dark energy, galaxies will be pushed ever further apart. The largest and most active galaxies will eventually consume their gas reserves, their star formation will cease, and their central black holes will quieten, shutting off the universal ultraviolet background. In a future so distant it defies comprehension, the last stars will flicker out, and the cosmos will become a darker, colder, and far more empty place. In this frigid, expanding void, the conditions for recombination might finally be met. With no new ultraviolet photons to tear atoms apart, the sparse, cooling gas could slowly begin to recombine, reforming a faint, neutral fog across the cosmos. It would not be a swift event like turning off a light, but a gradual fading, a slow sinking into stillness over trillions upon trillions of years. The universe would not return to its primordial state, as it is now far less dense, but it could achieve a new kind of neutrality, a silent and final twilight. This potential future paints a profound and cyclical picture of cosmic history, from a dark beginning to an age of light, and perhaps eventually to a dark and quiet end. The Great Reionization, the universe's single greatest awakening, might one day be nothing more than a temporary blaze of glory in an eternal night. 25 profound mysteries define this cosmic turning point. We have journeyed from the identity of the first light sources to the precise timeline of the dawn, from the hidden legions of faint galaxies to the great escape of their radiation. We explored the patchy, uneven nature of the clearing fog and the violent role of quasars and their supermassive black holes, born impossibly early. We felt the lingering heat of the intergalactic medium and hunted for the ghostly fingerprints of the first stars in the chemistry of ancient suns. We listened for the 21-centimeter whisper from the hydrogen fog and understood how the universe shifted from opaque to transparent. We saw the invisible hand of dark matter shaping the stage and grappled with the blurry, protracted end of the era. We decoded the polarization in the cosmic microwave background and uncovered how cosmic feedback suppressed the smallest galaxies. We unraveled the two-part drama of hydrogen and helium reionization and probed the molecular origins of star formation itself. We confronted the tension between supercomputer simulations and real observations. We witnessed the promise of the James Webb Space Telescope and the future Square Kilometre Array, instruments designed to finally illuminate these dark ages. And we followed the ultimate fate of the first galaxies and even pondered a far future where the universe might sink back into darkness. This era was not a minor footnote in cosmic history. It was the pivotal chapter that determined the very architecture of our modern universe, setting the stage for the formation of galaxies, stars, and planets, and ultimately for us. The next decade of observation promises to transform these 25 mysteries from questions into answers, pulling back the final veil on the universe's greatest awakening. As the data streams in, which of these cosmic secrets calls out to you the most? Was it the nature of the first starlight, the fate of the galactic pioneers, or the possibility of a second cosmic dark age? Share the mystery that captures your imagination.